So hello and welcome to Lab 2 Recitation. Lab 2 Recitation is all about random wanderer, avoid obstacle, and follow object. This week you will make your first of several state machines in your journey to build a control architecture on your robot. The objectives for today are to create a random wander behavior on the mobile robot, create an obstacle avoidance behavior on the robot, create an object follow behavior on the mobile robot, use potential fields to create the collide, avoid, and follow or wander behaviors, which are shy kid, aggressive kid, and curious kid, and then create a smart follow behavior and a smart wander behavior on the mobile robot. So think about what avoid obstacle means. There are several ways to avoid an obstacle. One way is if the robot is moving, is just to stop. The other way is for the robot to move away from the obstacle. There are various ways to do this, and the ways we're going to do it are potential field navigation. And then in a couple of weeks, you're going to see that we're going to integrate smart wander or avoid obstacle with go to goal, where your potential fields now have not only a repel force, but also an attract force, where you're repelling the robot away from obstacles, but you are drawing the robot into goals. So think about your mobile robot as a disk where the sensors around the robot, in your case, the 4 LiDAR and the 2 sonar, create a world around the robot that gives you a distance and an angle to an obstacle. And you are going to determine whether the obstacle is far enough it can be ignored, it's in the warning area, which means it's getting a little close to the robot, or it's in the danger area, which it is so close to the robot it needs to be addressed. And based upon the angle and distance to an obstacle, that dictates how the robot avoids that obstacle. So you can represent this with this trig statement, x1 equals x plus d1 cosine phi1 plus phi, where the robot's position is x, y, and phi, and the angle and distance to an obstacle is d1 phi1 or d2 phi2, and y1 is y plus d1 sine phi1 plus phi. So what you will then do is sum the vectors to avoid the obstacle. So you figure out the angle and distance of each obstacle, and obviously the closer obstacle would get priority. So if there were multiple obstacles around the robot, then the stronger repel force is for the obstacles and directions that are the closest to the robot. So steer the robot in the direction and orientation of the summation vector so that it looks like it is intelligently moving away from obstacles. So the way you do this is called a perception polar plot. In this case, our image would be a robot that has a sonar ring with 8 sonar around it in a circle. So it's now detecting, and if you look at this, the sonar 2 shows that that obstacle is the closest to it. So when the repel force, based upon the field force, then that robot should move in the direction of sonar 7, or one of the sonar that does not seem to detect anything, in order to get away from the obstacle that is detected by sonars 2 and 3. Looking at this as part of a subsumption architecture where the input is sensing, and you have a field force which is detecting objects, as well as a collide force. So collide would be for the danger zone when the obstacle is really close. That's halt, stop moving. Then feel the force and run away. So now you may have a robot that's either moving forward in a random wander behavior, but it's now going to be subsumed or inhibited or summed with the turn, so that it intelligently moves forward but also moves away from the obstacle. So what you're going to do for lab is level 0 of your subsumption architecture is going to be avoid obstacle, where you're going to have a sense, a plan, and an act, where your sense from the front sensor is, if I'm moving forward, the sonar or LiDAR in the front detects something, collide behavior triggers, or it just stops. Then using all the sensors, you're going to feel the force, and now after you stop, try to run away. So you now will dictate the robot's turn angle based upon the location of the obstacles, so it now moves away. The reason this is important is because an obstacle may not only be in the front, but it may also be in the front, left, right, etc. So you have to take all of that into account before the robot moves away from an obstacle. Another way to think about this is we call it aggressive kid, when the robot moves forward, stops, and then when it tries to move away, We call that shy kid because now it's not aggressively moving towards the obstacle, but it's trying to maximize the different distance away from the obstacle. Another example of a level 0 behavior would be follow object. For this, the collide behavior is exactly the same. The robot may be moving forward or randomly wandering. It gets really close to something. It stops to keep from hitting it. And now after it feels the force, it goes, I'm curious to know more. So instead of running away, it now tries to track at a certain distance, typically some safe distance. So this is now an integration of aggressive kid and curious kid. And now your state machine will be when you add that obstacle avoidance onto your random wander so that instead of just moving forward and stopping and either tracking or moving away, it now has a mission to explore the environment, randomly wandering, unless the priority becomes not hitting something in the environment. So it goes into avoid obstacle or it goes into wander. So we call these two control schemes bang bang control and proportional control. So moving forward and stopping when you detect an obstacle is called bang bang control because the controller is either on or off. Robot is either moving forward, no controller, or it just stops and the controller triggers or turns on. Proportional control would now be runaway or follow behavior where the robot moves forward proportional to trying to track an object, or it moves back or away proportional to trying to get away. Proportional control means the difference between the distance you want and the current distance makes the robot either go faster or slower, motors move faster or slower, or distance is bigger or smaller or slower. So that means the robot will not always be moving at the same distance. It will not always be moving at the same speed. It is proportional to how close or far it is from an object and ideally where the robot wants to be. Always think about your controller as trying to take your error to 0 based upon whether the error is the distance in the safe zone, distance in the warning distance, distance in the danger distance, etc. So once again, the first thing you're going to do for lab is just purely random wander with no consideration for objects or obstacles, which means it will hit. Green LED should be on. Next, your robot is going to do the collide behavior. Collide behavior is move forward and simply stop if it detects an object. That's it. Red LED should be on. Next, that's your bang bang or your on-off control. Should be your proportional control is your runaway behavior. That's your shy kid. Your yellow LED is on. And now it is moving away proportional to where it detects obstacles. Please make sure your robot can handle 1, 2, 3, or 4 obstacles. Yes, we are going to put your robot in a box and see can it handle what to do if it has an obstacle on all 4 sides. Yellow LED should be on. Here is an example of a halt or collide behavior.
So fast. What happens if you pick the trash can up?
It'll keep going. I'm sorry.
Very good. Trash can down. You have a very aggressive robot. Is this IR sensors?
Yes.
Yes, but we were getting, but I'm just saying it was inversely related to distance.
What distance did you stop at?
4 inch.
4 inches. What happens if you lift up the barrier?
It will keep going.
All right. Good job. Collide. Very good. Sonar IR.
And then we can adjust the.
Gorgeous. Lift her up. All right. This is halt collide behavior. Red LED turns on.
If I put it here, I'll do it while it's
The
moving.
heading is going to be into.
No. Just stop and then.
So now that was an example of the halt or collide behavior. The bang bang controller means the robot should start back moving if the obstacle is removed. Now let's see what potential fields looks like.
At least mine are Rose students. Okay, all right. I'm ready. Do not kick my baby. And the walls come tumbling down the walls.
Put your wall here.
All right.
Turn it on.
So boot it up.
It's gonna go straight, I promise. It's not going straight.
Womp womp. Okay, let's try it again.
It did, but it weren't looking.
It worked that
That's
one
the
time
part.
when I didn't have the camera on. It's
That's
got
the best part.
it's got camera
Alright.
fear.
Don't make people.
Are you sure your walls? Womp womp. Are you sure your walls are not too far away?
I set the threshold within 6 inches, so make them a little closer.
Okay, that's a little closer. Yeah, that's probably better.
That's probably good. Thresholds are set for about 6 inches. Yep.
Yeah, that looks
I
good.
can bump those up.
All right, now he turned that time. Now can we turn it off and start him up with front and back on?
Yep. It's gonna turn left. You're gonna want to slide it slightly out.
It always goes left
Yeah, it'll always go left for this condition.
or not? Why did it go forward first? What was that
Really
about?
good question.
All right, let's try that one again.
Did I forget to pull up?
And here's another example. So remember, as I said, your robot needs to work for all iterations of 1, 2, 3, 4 walls.
Very good. Can you get one of these L walls and show me front and left, front and right, back and left, back and right?
So this is front and left.
Front and left.
It backs up and then it's sort of in a dead zone.
Okay, front and right.
It should also back up here.
Okay, very good. Back and left, back and right.
This is back and left.
Okay, last one is back and right. Okay. Now we need front, back, and left, right. So front and back. So get one of 2 boxes to make front and back. Yeah. Yeah. All right, front and back.
I'm going to use the longer one here.
Okay.
Yeah, it needs a little room to turn.
Woo, he's threading that needle. He did it though. All right, left and right. You should just, in theory, just drive straight out of that. Very good.
So now, how about follow behavior, which is curious kid? This is something new for this year's lab, so we don't have any videos, but what you need to think about is that this is getting us ready for wall following, where now you're using proportional control to try to maintain a given distance from the robot. So for example, let's say the robot is less than 3 inches from an object, it should just be in collide behavior. Then it should back up to try to be in a window, let's say 4 to 6 inches from an object, and maintain that distance. So if the object moves, it should track that object to try to stay between 4 and 6 inches, where it speeds up and slows down proportional to how far or how close it is from the object. The green LED should then be on, green and yellow, because green LED is random wander. The green and yellow LEDs should be on for this behavior. Once we have our full state machine working, you should now see that your robot should be able to move randomly in a cluttered environment and not hit things. That's the important part. Because there are sensors all the way around the robot, no matter what is triggered, the robot should try to randomly wander while avoiding those obstacles. So here is an example of what proportional looks like for goal to goal. One question I've recently received from my Twitter trivia, robotics fun facts, and engineering fun facts is, How does potential field navigation relate to proportional control? So I just wanted to make a quick video to explain that. So in potential field navigation, obstacles are seen as a vector with a magnitude and direction that pushes the robot away or repels the robot, and goals are seen as a vector and a magnitude that draws the robot in. So if the robot moves proportional to either the goal or the obstacle, that is the same as proportional control, where you have a set point and based upon the error, it adjusts how the robot moves. So think about it like it's either pulling the robot in to the goal or it's pushing the robot away or repelling it. I'll show you a sample graphic of what that looks like, as well as some code. Full speed ahead, halfway there, getting close, and stop. That's proportional control. So this loop implements proportional control, potential field navigation for go to goal. The first thing it does is it finds the difference between the current time and the beginning of the code runtime. And if that time is less than 10 seconds, the robot moves full speed ahead. If it's then less than 15 seconds, the robot is halfway there, so it slows down. If that time is less than 20 seconds, the robot is getting close, so it slows down a little bit more. And then once it is greater than 20 seconds, the robot stops. One question I've recently, and here's an example of obstacle avoidance using proportional control. So you can also use potential field navigation or proportional control for obstacle avoidance. And the way this works is that you represent the obstacle as a vector that's pushing the robot away. So when the robot is really far from the obstacle, it goes at full speed. And as it gets closer to the obstacle, it slows down in order not to hit it. You can also think of potential field navigation as a way of repelling the robot. So that if the robot's already close, it pushes it back. So you can look at this two ways: a robot driving in and slowing down as it gets close to the obstacle, and then driving away and getting faster the further it gets away. So let's take a look. All right, here we are full speed ahead. And then as the obstacle gets closer, proportional to how close it is, the robot slows down. And then when it gets within 5 inches, it stops. Now, obstacle avoidance is not only about not hitting, but moving away. So it's going to move away slowly, and as it gets further away, it moves away faster. Then once it's in the clear, it stops. Let's try that again. Full speed ahead. Then it slows down as it gets closer to the obstacle. Slower, slower. Too close, it stops. And then eventually it's going to want to back away. The further it gets away, the faster it goes until it's in the clear. And that's proportional control for obstacle avoidance. So this loop implements the proportional control. The first thing that happens is we use a variable to read the distance. We print the distance for debugging. Then we set if the robot state is moving toward the obstacle, then it's full speed ahead if the distance is greater than 15 inches. Then it is halfway there if the distance is greater than 10 inches, greater than 5 inches, getting close, and then less than 5 inches, the robot stops. Then we set the robot state to 2 to move away. We wait to read the sensor again. And in move away state, if the distance is less than 5 inches, we will move backwards. because we're close to the obstacle, then a little faster as we're getting further away, and then when it's less than 15 inches, it's full speed away. After that, the robot is stopped because it's clear of the obstacle. And here's an example of simulating the state machine where you now have random wander with avoid obstacle. And notice that the vector lines turn red when the obstacle gets really close, and then it is moving away proportional to that distance. And this is what your robot should be doing when it's in full state machine for either smart wander or smart follow. And so once again, if we look, you're not going to do go to goal for lab 2, but you will do it for lab 3 or 4. You're going to have a world of potential fields and obstacles repelling, as well as a goal attractor force. And so your robot would be moving from T1, T2 to the goal while also avoiding the obstacle as shown in this image. And here's an example of smart wander.
All right, so green LED means random wander. Red LED means halt. Yellow LED means avoid. So we know what the robot's thinking by the color of the LED. I don't know if the LEDs are changing colors. Put it back in front, Jake. I see the green LED going off, but I never see the red and yellow LED turn on.
The red's off. The yellow's turning on really fast.
Oh, it's turning on really fast. What did you say about the red?
My LEDs definitely turn on.
So are you telling me to stop besmirching your LEDs? Okay, Jake. They turn off. I just never see another color turn on.
Yeah, it's turning on really fast.
Oh yeah, I see it. I see the yellow. I saw the yellow one.
Yeah, the yellow's really fast.
And I think red just doesn't happen because it stops for like so quickly. Random wander with obstacle avoidance. Can the robot avoid itself out of the garage? Let's see. Good job. He's randomly wandering, but he recognized he was in an obstacle from the very beginning. He's now randomly wandering unless he sees an obstacle. Good job, Gord. Okay, go ahead. A whole new world. This robot is randomly wandering, but it should not hit obstacles, so it's really smart wander. Green LED is random wander. Yellow or okay, go ahead. A whole new world. This robot is randomly wandering, but it should not hit obstacles, so it's really smart wander. Green LED is random wander. Yellow or red LED is avoid obstacle. Red LED is collide behavior. Yellow LED is run away.
It's usually forward rather than
Yeah.
I see the yellow. There we go. And then let's see if I get away from it. Does it switch to green? Okay, yeah, you need to. The robot is randomly wandering in a tight space. In theory, it's avoiding obstacles. The LED is green when it's randomly wandering, and it is yellow when it is avoiding obstacles. Right now, it's yellow all the time. Okay, I just saw it switch to green. He's trying not to hit things, but there are dead or blind spots on the robot sensors. So when that happens, it's gonna hit. Very good. Furby is done with Smart Wander. So now, to make your software design plan, remember you could do pseudocode, you could do a state diagram, you could do subsumption architecture. So let's just do a very brief overview of a flowchart. A flowchart is a great way to sketch out how a circuit or code should work. It's a way of devising your algorithm, where your flowchart is a game plan. And a flowchart may have circles, diamonds, squares, and lines, where a circle denotes starting and stopping. Squares is an action with one outcome. A diamond represents where a decision may be made with multiple possible outcomes, and lines connect all the parts of the flowchart so that you know the way that the process happens. A flowchart can also be called an algorithmic state machine, where you have a state or an action in a rectangular box. Then the output variables are included in a box, and then you have a condition or a decision, and then you output, and then that is something that denotes a start or end. Note that you could have a mealy or more state machine, where the more machine outputs based on the state input, or a mealy machine generates outputs on state transition. There is always an entry point. There may be 0 to many exit points. The entry point for our robot will either be driving forward or random wander. Here is an example for a flowchart for getting up in the morning. You start, you look at the time and decide whether to get up now. If the answer is no, you hit the snooze button and sleep more. If the answer is yes, you then have to make decisions about the bathroom. Yes, floss. Yes, brush teeth. Yes, shower. No, smell bad. Then you decide, are you ready for today? Yes, that's the end of the process. No, you go back to use the bathroom and maybe start over. Here's an example of a flowchart for a stopwatch. It is related to the flowchart from Lab 1 Recitation, which was pseudocode for a stopwatch, where it now comes up in a state 0, where the counter is 0, reset is 1, and run is 0. And then you decide if the button is pressed. No, then you stay in that state 0. Yes. Then you go to the run state. You increment the counter. Reset goes to 0. Run is a 1. Then decide if the button is pressed again. No, then you stay in state 1. If it is, then you go to the stop state, and the counter is set to its final value. Reset is 0. Run is 0. And then you make a decision about whether the button is pressed. Again, if the answer is no, then you stay in the stop state. If the answer is yes, then it goes to state 0. A state diagram can be used to describe the behavior of a system such as a robot as well, where each circle represents a state of the system, and you represent the net effect of all previous inputs on the system. Where you have a previous state, you put in an input that sends it to the next state, and then the output of that sends it to the subsequent state. So here is the stopwatch that we showed as a flowchart as a state diagram. It has 3 states: reset, run, and stop. If the button is pressed, it goes from reset to run. If the button is pressed again, it goes from run to stop. If you're in reset and the button is not pressed, it stays in reset. If you're in run and the button is not pressed, it stays in run. If you're in stop and the button is not pressed, it stays in stop. And if you're in stop and the button is pressed, it goes to reset. Here is a state transition table for a basketball shooting robot. So you have the states as the robot starts and detects the basketball. If no basketball, it stays in that state. If a basketball is found, then the robot moves to the retrieve basketball state. It will stay there until the ball is retrieved. Then it goes to the find goal state. It will stay there until the goal is found. Once the goal is found, it shoots the basketball. It then tries to detect if there are more balls available. If there are, then it goes back and starts over. And if not, then it ends. For a state transition table, you would list all of the states as shown here. Then you will have the input, and based upon that input, you show the next output. And you show the next state. So for your pre-lab, you are going to make pseudocode, you're going to make flowcharts, and you're going to make state diagrams for different possible behaviors or actions on your robot as stated in the assignment. Here's another example of a flowchart for a robot boogie machine, where the robot starts, you input the music. If the robot detects the music or the type, and it's not one of the ones that it can dance to, it returns to input music. If it is, then the robot does that. If it's ballet music, the robot break dances. If it's classical music, the robot does ballet. If it's country music, the robot does line dancing, and then it ends. And here is an example of the state diagram for the robot boogie machine, where the robot is waiting for music is one state, the robot line dances for one state, the robot does ballet for one state, and the robot break dances for one state. And based upon the input, it transitions to the appropriate state, whether it's country for line dancing, hip hop for break dancing, or classical for ballet, and so on. And here's what the state transition table from the robot's perspective would look like. It's either waiting to dance, or it's break dancing, line dancing, or doing ballet, based upon whether there's no music, hard rock music, hip hop music, country music, or classical music. So the way that we implement a state machine in code is we either use if conditions or we use a switch case state. Here's an example with if conditions, where we define the states for the stopwatch example, reset, run, and stop is 0, 1, and 2. And then if the state is equal to reset, we check for the button pressed and implement it to the next step, and so on. And here's an example of implementing a switch case example of a state machine, where you have a switch state, and based upon the case, you then do an if condition to make a decision, and then you implement the next state. In this case, if your button is pressed and you're in the reset state, it goes to the run state, and so on. Note that switch case is a different way of implementing an if-else condition decision making, and that you must use a break if you're using the switch case option, and that you need to have a default if none of the cases matches. So what are you going to be doing for pre-lab 2? You're going to create pseudocode for the random wander behavior, a flowchart for the proportional control with sensor feedback for the avoid obstacle behavior, a flowchart for a proportional controller with sensor feedback for the follow object behavior, a state diagram for smart wander with 3 states, random wander, collide, and avoid obstacle, where the inputs to transition to states are no obstacle, danger, obstacle distance, warning, obstacle distance, and also a state transition table for that smart wander behavior state diagram. Then you're going to create a state diagram for the smart follow behavior with 3 states, including random wander, collide, and follow object, with the inputs same as before, no obstacle, danger at obstacle, warning close to obstacle, and a state transition table for the smart follow behavior state diagram. Lab demonstrations will be in 2 phases, just like lab 1. The first phase will be do the class after the lab recitation, and it will be robot random wander, robot collide, robot runaway, and robot follow. No state machine at this point. Show that you can get each of these behaviors to work individually. Part 2, which will be due 1 week after the lab recitation, will be the state machine, subsumption architecture, robot smart wander, and then robot smart follow. So your demonstration requirements, once again: aggressive kid by itself, shy kid by itself, curious kid by itself, random wander by itself. Then the integration of avoid, obstacle, and follow object, and the full state machine, smart follow, and the full state machine, smart wander. As always, there's 2-phase demos. Your memo worksheet will be due the Sunday after all demos are complete. Make sure your code is properly commented with line comments, header comments, block comments, and that it is modular and that you are reusing functions as necessary. That will prove very helpful as your code becomes more complicated. Your code will be submitted in the appendix of your lab worksheet. Please go see your professor or the teaching assistant if you have any questions, and happy roboteering.